right? So what we're trying to do is have something more sparse that doesn't need as many connections as a fully connected one, because there's a lot of pixels and we probably don't need all of them. We need to have something that's going to represent a local area of pixels. So how does that look in a in our normal fully connected one, right? Essentially, we had this where this could be the input layer, and this could be the first hidden layer. Right, every node is connected to every previous node. That's what I was drawing before. So you could have any level, any type of connectivity, right? You could just decide that every node only connects to the ones near it. And so you have some kind of local connections and just get rid of them, and that each of these weights are separate and individual. People don't usually do that. The main idea here, what they're trying to get at, the next figure shows it better. What convolution does is says that for every node, the weights are being reused. So we can have any kind of reduced the weights are shared across all the different locations. Sorry. I don't know why it's doing that. Okay. Weights are being reused. That you could basically learn. There's really only in this model, this very simple one. There's only two weights in this layer, A and B. They're really just two numbers, A and B, and you're trying to find when you're doing backpropagation and optimizing the weights to maximize your accuracy or minimize your loss. For this particular layer, you'd be trying to follow the gradient and improve the values of A and B so that they satisfy all of them together, right? So a more correct way to show it for CNNs is like this, right? So for every pixel here, we've got a filter that connects to a neighborhood of some other pixels. And like we had before, you could literally name these weights, and that would mean then that the other nodes nearby would have the exact same weights for their three, right? And so you're trying to find the settings for these weights that learn a pattern that works across the entire image, right? So one way of thinking of it is that you've got this filter which applies on a local area around pixel 3, but then you shift it, you slide it around the entire image and figure out what its response is, and that's what you get, the output for the next layer. And this is a lot less links, right? So if you just talk about doing dense versus this, we're getting rid of a huge number of them. And the argument is that for an image, this is all you need, because the fully dense one is unnecessarily connecting pixels at one part of the image way over to the other side of the image. And technically, that you can probably have patterns that are more local, right? So good question in there. Hyperparameter tuning. Wasn't planning to have a whole section currently. We don't usually do that as a whole section, but that could be something I could try to talk about next week a bit. So that's a good question. So Jugal's got a question about tuning hyperparameters, because these days, if you're just assuming you're using the network, the libraries to train these things directly, the question for you more is not what is a neural network and how to design it, but how do you train, how do you decide on the hyperparameters of your model? So how many hidden layers do you have? What kind of function, activation function do you use? Other aspects of for CNNs, there's quite a few about how much these filters overlap in something, which we're going to show. I can try to say something about that next week. I'll look up some things and give you some of the recent things. But I mean, it mostly comes down to tuning of the, essentially doing experiments to see which ones work better, right? So doing like cross-validation on one set of it, and then trying different values and trying to search for the right settings for the hyperparameters. So trying out different layers, different numbers of hidden layers, and then seeing which ones work, or changing some learning rate variable, and experimenting on a kind of validation set. There are methods that do more optimization and try to search that space more comprehensively, and that's kind of beyond the scope of this course. But yeah, we're going to talk about filters now. Okay, so yeah, a couple good questions there. How do filters work, and how does backpropagation change when a single parameter is used in multiple edges of the network? Okay, well, hopefully that will become clear once we see how the math works out here. Let me get my other slide deck in case I want to switch to that. Right, okay. So the main part of the convolution is this, where sorry, I should have loaded my head. We've got a, what is it? Bunch of weights, A and B, M and N. What is it? So it would help if I remembered what all the numbers meant. We've got a bunch of weights where what we're trying to do is represent that local neighborhood for every pixel, right? So in this case, we've just got a very linear set of weights. So for some pixel, I don't remember the exact notation of this, sorry. For some pixel ij that we're currently at, say you had two matrices of weights. This next one is clearer. So here the input image is I, and K is our kernel. So when we're talking about this filter, oh, it shows it even better. So we'll get to that one after. When we're talking about that filter, we're talking about this 2D kernel, and this is some set of weights that you're learning about how a pixel, or how pixel I relates to pixel j, right? And so if you flatten the image out, so you could have a a 50 by 50 image, and we'll flatten it out to be just a flat image. So I is just going to relate to the actual pixel directly, and j is some other pixel. this matrix K is going to tell you how much that pixel relates to, the pixel that's 2 down from it, right? So if you're at this location, what's the one that's down, over 1 and down 1? So you have a matrix of all of those values. And you multiply them together. So for every value of your actual output pixel, this would just be, if we're talking about a grayscale image, it's just going to be the actual number, 0 to 256, or you probably normalize it to be 0, 1. And then this will give you a weight on that many, the kernel, right? So we're saying here, if the pixel is mn, this kernel represents all of the locations around it, right? So you have to subtract the actual center of the image, the center of that pixel, from the orientation, right? So in our kernel here, right, say we have a four value kernel, then we're talking about for every pixel that you have, for every location you start the filter at, so we've got this starting at filter at location 1, we've got 4 values that we can represent it with, right? So for every pixel, A, B, E, and F, we multiply it by the weight in that filter, and we get this one value, right? And so if here we have input pixels A to L, right? These are the inputs. For every one of these, we're going to get a new value that gives us this new output, right? So now the value at this node is able to basically deal with, it uses the responses from A, from B, from E, and from F, but it skips all the other pixels, right? And that's the output for this one, right? And so each one of the pixels and each one of the nodes in the second layer, the hidden layer, is only using some of the pixels from the previous layer, but they're arranged in a spatial grid, right? So you might jump down the list, so you're skipping C and D here, but that's because they're not spatially beside that pixel, right? So mathematically, for every image, we're basically doing that, and if we treat them as matrices, we're just multiplying them together, but centered at that location. And there's no difference in terms of the output. What happens next here? Because basically what we're happening then is that this next layer is now just another layer that has a bunch of outputs, right? The fact that it's only getting connections from some of the inputs doesn't really matter. You can still represent that response at the hidden node by that function, and it's important that each of these parts is still differentiable. So the kernel itself is just being combined as a weighted sum, so the gradient will work the same way. Yes, yeah, there can be multiple. That is an important part. So this other slide deck has that. It's hard, it's like not always easy to know which one to, which aspect to start with. So in this other, does he have it? Sorry. Okay, actually, the other deck still has it better. So, so if we just had a single layer, we've already talked about parameter sharing, with a very simple kernel, you could imagine, right, that we're going to have this kernel and say we only have one of them, like I'm talking about here, and you're applying it on this image. Basically, for every pixel, you would pick, a response of 1 for that pixel, and then a -1 for the one beside it. And so the response, if you think about when would this be high, this would only be high when you go from something where there's basically a high value, so bright, right, like white, to a low value, right, so black. And so whenever this occurs, this kernel would give you a high response, right, because you wouldn't be wasting the values. If it has white on the second aspect of the pixel, for every pixel, you're taking that and you're taking it to the pixel beside it as the two inputs. For every pixel here, we would end up getting a second layer where there's a single number that's the sum of these. And that just gives you a simple kind of edge detector, right? Which says, basically, if you see lines going in this direction on this image, you're going to highlight them as bright spots. So that's very simple. That doesn't really help us because we need to figure out what these kernels are. So the genius thing about CNNs, and which helps us get past what we had with SVMs and stuff, is that we're not just going to have one filter. And that's what Chris is pointing out in the chat there with people. For everyone, this feature map I'm talking about is a single filter here that we've been learning, right? So you've been learning this. I was trying to draw X, Y, Z thing, but you learn some filter here that applies to every pixel. But you can have many, right? So you'll start off usually with like 64 or a large number of them. And each of them are initialized randomly. But then as you're learning, they can differentiate to learn different things, right? And so each of these layers here could learn something like an edge detector, or some color is more important than other colors, or something like that, by looking at local response functions of these feature maps. And the other aspect that I had earlier is these are all black and white, so you'll also do that on multiple colors. Okay, so let's go to that other figure, because they have a different way of showing it. Yeah, and so people talk about, okay, so we'll have some questions. Does the asterisk mean a convolution? That's very specific. So people are talking about the idea that lower layers have certain patterns in them or not. Oh, right, okay, so that was, all right, she has a specific question about the asterisks here, they mean pairwise multiplication. I think that's why, right? Because you're basically literally taking each pixel and just multiplying it by the corresponding one in the filter. So you've got to offset it. So you take this pixel and you, if this filter is a 3x3 filter, then for every pixel you offset and go -1, for the first element and multiply them as a matrix centered on the current pixel. So it's not matrix multiplication directly that way. Yeah, we'll get to this idea of simpler versus more complex filter features soon, because it comes out of the way people build them. It's not inherent, as somebody was pointing out. So what we're still doing is basically we got a bunch of weights, and we're trying to learn them, and then we're going to have our oh, okay, right, it's fully connected. So the normal deep neural network is like this, right? You have some weights you're learning, you do matrix multiplication on them, you have a nonlinearity, and then you multiply again, and you get some outputs, and you have some number of hidden layers, right? In convolution, we're going to do something different. So rather than multiplying the matrices and getting all combinations, we're going to do this convolution operator, where we do pairwise multiplication on a smaller filter and slide it across the image to get these outputs. But then we're still going to have nonlinearities like we had before, but we're also going to have something called pooling, which is going to change the size of the outputs. So let's see if he explains that here. Right, so our filter that we're talking about now, we could have 5 by 5, say, and this is X, Y, and we're assuming it's a color image, so we've got RGB as your 3, right? And so the same for the filter. There's different ways you could do it, but one way to do it is that you have basically a bunch of filters for every color. So we're going to have 25 filters for every color and let it learn them separately. And like we said, we're going to slide them over the image. But you want to have enough variation here so that you have filters across the different layers and the size of it so that you can learn enough patterns to learn what's going on in the image. So if you don't consider color, then you'll miss a lot of things. Right, and so every output in this next hidden layer is going to be the result of running some particular filter at a particular location, some particular filter across the entire image, and getting that output. Well, it's run at every location, sorry. So you run that filter at a particular location and you get an output, but we train the weights across the entire image, right? Because basically every one of the nodes that are for that filter in this hidden layer will be sharing the same weights. Yeah, then we'll do pooling. So once you do that for every pixel and all the filters, you're going to get a new kind of image, which is the activation map. Well, each filter is going to create one of these, right? So if we have this many filters, but for every one of those filters, we'll produce an entire new image, right, of roughly the same size. Now note that it's not exactly the same size. People could probably think of why that is, right? If we've got a 5 by 5 filter, what do we do at the edges, right? So what to do at the edges of the image is an issue, so that has to be dealt with, but we'll do that a little bit after. Basically, you have to throw away the outer pixel because you'll never be able to have a proper filter on those. So the activation mask can be slightly smaller than the original one, but now you're going to have one for every one of your filters, right? So if we just had 6 of these filters, then we'd have 6 activation maps that each of them is producing an entire basically new image of the original. So like that dog picture I had with the edge detector, each of these would be maybe a different type of edge detector, right? And these can all be treated that way. So now we have this pooling, which is the other new thing that CNNs have that deep learning doesn't have. And these are really just downsampling. Because what you're taking is the outputs that are a certain size and making them smaller, right? So if we have an image that's that size, we're going to make it into a smaller image. And specifically, okay, just as an example, there's specific ways of doing it. Obviously, you could average them all together and give you a value, but each of those would be its own type of pooling. So max pooling is one that's often used as a default, and so this doesn't take the average of a set of points, it takes the maximum, right? So you can take the strongest response for every set of some size. So if we're going to do a max pooling of with 2 by 2, so basically reducing the size of this data, the activation maps by half, we could use max pooling, and for every set of 4 outputs in the activation map, I was going to say pixels, but they're not really pixels anymore, you just pick the max one and then you get this new one, right? So you could take the min, you could take the mean, you could do something else, but max is very simple, it's fast to do, and it gives you the strongest response, right? So it really says, like, in this neighborhood, what was the most important thing you learned, right? And so it learned these things, and so those become the next layer. So this next layer now is going to be smaller, obviously, and that will give you smaller pictures, these activation maps that are essentially just summaries of it. And the way that CNNs generally work then is that you do convolutions on the raw image with some large number of filters to get the color and the initial structure out. Then you subsample so that you're getting rid of maybe some noise or things that aren't as important that are being learned. So you're focusing in on the core features. And then you do convolutions again. So you learn new filters. These are completely new ones. So if these are like the W1 weights, these are going to be the W2 weights, completely independent filters. They could even be different sizes than the other filters were on this image and again. And you can subsample. You can do this as many times as you want. It's common just to do 2 or 3 and then switch to a fully connected network, right? So this question of getting different levels of complexity so that the earlier stages give you, Jogel was saying, color, edge, shape, texture. But then, right, so the neural networks are black boxes, so how do we know it does that? So well, we can visualize them, so we're going to do that. I'll show you pictures. Both slide decks have it, but the other slide deck, Justin's one has some good visualizations of it at the end, if you want to look at that. But why would it do that? So that's not by design. Actually, maybe show you. Yeah, so that's what everybody's discussing. So let's just jump to it then, or if I can get my other thing open. Because, yeah, let's jump to that, because the next couple slides here are talking more about the history and standard methods that were used for putting, like architectures for putting these together. So we can come back to this, because there's ways of chaining them, but they become very big very quickly. I guess an important part of pushing for deep learning was that CNNs worked only so well with just like these 3 layers, but getting much deeper ones was leading to a lot of improvements, but they were incredibly computationally complex to use, right? And so people were trying to improve that, right? Time's going up here, so they're this is the error of the best winners of that competition in that year, and the best ones are on the left, so you need to read it in reverse to what you normally do. And they were finding more layers were working, but in order to get that many layers working, you had to do these other tricks. But what people are talking about in the chat here is visualizing, and I think that can help understand what's going on a bit. So if we take AlexNet, so that was that first one that we showed as I skipped through. So let's just look at that then. So AlexNet was this first big one in 2012 that really broke the system for the competition people were using with other algorithms and making incremental improvements, and then they made a huge improvement. So how did they work? So they've got, you have to learn to kind of read these kinds of diagrams now, but usually people just write it down as numbers. So they'll talk about the standard components to tell you how you'd build this architecture. So when we talk about all of these, I guess these are hyperparameters as well. The design of a particular network, we call that the architecture. And the model is the weights that it actually learns, right? So like layers, pooling, type, stride, which I'll explain now. What's the other one? The stride and the thing about the edge, padding and padding. These are all parameters. Sorry, that as you were asking about, right? What are all the hyperparameters of the architecture? But if we talk about the model, which maybe people are wary of saying model because it can mean so many things, but these are the actual weights that are learned, right? Because that's actually what how the thing does its detection or its classification. So in their model, in their architecture, see, I did it myself. They have their initial input, then they have 48. Let's just read it off. 227 by image and 3 color channels. The first convolutional one had 96 layers with 11 by 11 filters. So that's pretty large. A lot of times people will use just 3 by 3 or 5 by 5. So stride 4 and padding of 0. So what does that mean? Later on in this original deck, there's a why it works, downsampling, we talked about that, some examples. Okay, so right, strides are the number of overlap between adjacent filters, right? So if you have pixel I and pixel I plus 1, should their filters overlap by 1 or by 2 or by none, right? So if you want no overlap, then you can have stride of 0, and basically all your filters then would only work on contiguous, on like a partitioning of the image. Strides so usually are is usually more than 1, because it's kind of weird to say no overlap, but like 1 or 2 are normal. And then padding is about how you deal with the edges of the network, right? So you basically set the edges of the image, sorry. You set the edges to 0 so that they don't impact it, right? So you've got your original image, this is the image, and this is the hidden weight. I should just stop trying to do that. If you didn't do this, each layer inside would have to be much smaller. But what you can actually do is then just like add 0, add a bunch of zeros around your image, so that the image is a little bit bigger, but then your filters can actually fit within it, and you can use all of them. So these ones on the edge are still going to be kind of like a bit weird because they often have 0 beside them, but at least they'll still be able to learn something. But whether you're going to do that or not is a choice, right? So what parameter are you choosing for the 0 padding, right? So they had 0, so they didn't have any padding at all. And then they have a 3 by 3 filter for pooling, right? So this next layer after the pooling is now a lot smaller because they applied a 3 by 3 to it and create a new image and had stride of 2. And then they normalize all the values in that layer and they repeat again. So you can keep doing this, and they did 5 different convolutional layers. And on the later ones, these 3, once they've basically downsampled enough so they've gotten some kind of higher level features, they just did 3 more convolutional layers back to back with just feeding into each other. There's no reason to do this. There's no right or wrong. You can try to argue why it might be more useful after you've seen it, but it's really, you just hack and try it and then make an argument based on how it performs.